Okay, everybody, today's a big day. Oh, I'm gonna introduce a couple of quick guests before I introduce Reese. Jeff, do you want to introduce yourself to the class?
Sure. So my name is Jeff Rosenbaum. I'm one of our chief IT strategists at ExxonMobil. Just in town for a conference. Met Ravi this morning, and he invited.
I'll share some contact info. I'll share it in the group. All right, guys. Well, welcome. This is the last day of the class, but just the beginning of your careers as an entrepreneur. Okay, so the door is never closed. And the beauty with entrepreneurship is that there's never an end. It's always a perpetual beginning and a perpetual discovery. And so I figured there was no better theme to end the last day on than on what represents perpetual discovery, which for me is singularities, and the man who knows these better than anybody else, and that's Reese Jones. So we're going to have a guest talk from Reese, and then I'll close out class for the last 20 minutes. Does that make sense? Okay. How many people have heard of Reese Jones? Does anybody know Reese before? Okay, so Jeff has. How many people have heard of Singularity University? Has anybody heard of Singularity? How many people have heard of Netopia or Farallon? Okay, so Reese represents the essence of what high-tech entrepreneurship is all about, and a lot of what we try to capture at Stanford. So Reese is a biophysicist from UC Berkeley, okay? But he went on to go and be the founder, and then took public Netopia, which was $1 billion company in the wireless, in the wired networking space. Reese is a technologist at heart. He invented twisted pair wired networking communications, and then he was the founding CEO and founder of Netopia, also the founding CEO of Farallon. And he's been on the board of over like a dozen companies, and is currently was the associate founder of Singularity University, which he might talk about, as well as he's on the board of trustees of the Santa Fe Institute, which is a big think tank on complexity theory in New Mexico, as well as he's on the advisory council at Harvard for the Harvard Genetics Advisory Council. And Reese is a mentally kinetic soul who's constantly thinking, you can't really box Reese in because he's always thinking about applying technologies to whatever the changing landscape is. And so today I tasked Reese with just giving a final talk to the class. And I don't know if he's given this talk before or not, but I'm going to turn it over to Reese to take it from here.
So given that this is the last class of the quarter, thought I'd go a little bit more theoretical and abstract, as opposed to some bold stuff. If you want to remember one thing about this talk, is that there's many singularities. There's not one. The term originates from physics as the solution to Einstein's field equation in about 1916, and has been used in many different ways. More recently, people have been using it as when computers become smarter than people, or the internet does, what happens becomes unpredictable. But there's many different kinds of singularities, and what they hold in common is an acceleration towards something that is unpredictable or chaotic. So in physics, space-time, energy, and matter, a singularity is sort of a warp point in that has been evolved into or observed as black holes. This is a simulation of a black hole, what it would look like optically, where a black hole, the gravity is so strong that it pulls in even light in addition to all matter that's nearby. It's thought that most galaxies, the center of the galaxy is a black hole, and that's the attractor that holds the solar systems and dust and whatnot into the galaxy form. And you can see this is Earth's trajectory around our galaxy, and that's Earth at the top, and the yellow triangle is what the what the Kepler telescope can see as it's searching for other planets. So you can see we're a small fish in a big pond with a limited range of view, and far away from the singularity point of this galaxy. So how many of you have seen something like this before? So this is in a lake near here, Lake Berryessa in Northern California, and this is a singularity where the water from this lake falls into that hole. And you can be swimming around the lake doing normal things, and the experience of swimming will be as you expect it to be. But if you were to swim close to this edge, you would be sucked into that hole. And what happens to you would be unpredictable. So that's the definition of singularity. So what these things sort of sound like and look like is the water going over the edge of the hole, and there's a conservation of water in this case, in that the water doesn't disappear, it goes somewhere. And it's a spillway in the dam, and that is the entry point to it. So the water goes in, is mixed up, you would be mixed up if you fell in there, and come out, maybe okay. So another model of singularities or black holes is it's possible, or a reasonable theory, that the Big Bang is a singularity point for somebody else, and we might be inside somebody else's black hole. And so black holes, as we observe, might be Big Bangs for other people that we wouldn't be able to see. And there's arguments going back and forth with Penrose and Hawking and so forth about whether information can fall through a black hole and survive, or whether it gets scrambled. But more locally, there's the example here of the water through the dam, and people like to play with these edge cases, these singularity exponential changes. So here's a group of people jumping in next to an event horizon, and that event horizon is relatively stable, but if they were to move 1 or 2 feet back, they would go over the event horizon, and that's what it is. So what would happen to them is unpredictable. So that's an example of a singularity and an exponential change into unpredictability that you might experience. So other people say, well, what if I did go over that thing in a hack boat? So here's a guy doing it. This is about a 200-foot waterfall. So he goes into the chaos and the complexity of the turbulent water, and we don't know, does he die? Does he come out? Is he broken? Is he hurt? Has he disappeared forever, stuck on the rocks underneath? There's his friends at the bottom, trying to see what's going to happen.
Where are you, buddy? Where are you, buddy? Oh, he's out against the boat.
So he basically survived, but his paddle didn't do so well. And he's conscious enough to salute and then fall. So here he's trying it again on another waterfall. And this is going into unpredictability and chaos. Now you've heard about the white light of death. So that's a kind of experience. Well, that's a mystery, isn't it? That's a personal feeling of how it might feel to fall into a black hole or to fall into a singularity point. There are other kinds of, from a mathematical point of view, there's other kinds of singularities that people experience in normal life. This is sort of chaos theory applied to heart attacks, and our heart beats roughly once a minute or so, and if it were to beat to more than 4 minutes, we would die. So if you're just randomly varying the time between heartbeats, if it goes to its defibrillation or fibrillation or more or less stopped, in either case you die. So it's an example of an analysis of how a heart attack works from an experience point of view. So if you're sitting here in a normal circumstance and you have a heart attack, it affects your life immediately in an unpredictable way. You might not be able to breathe, you might not be able to sit up, you might soon die, you might get resuscitated, You might get resuscitated but incapacitated for the rest of your life, or be just fine. So it's going from a normal state to an unpredictable result. And it turns out there's a lot of things like this in life. Heart attacks, a stroke where part of your brain is turned off, a trauma of various kinds, birth in life. When a birth happens, what happens to that person afterwards is unpredictable. Death or near-death experiences are unpredictable in that you could be going through an experience that might lead to permanent death and maybe not. 100 years ago, death was considered when somebody stopped breathing. And then 50 years ago, it was considered when their heart stopped. And 30 years ago, it was considered when people's brainwaves have stopped. And now, Facebook, for example, has changed its policy to allow people their Facebook to live on even after their biological body is died. So the definition of what is dead is becoming unpredictable and perhaps due for a change. And that's a state change. And then there's other kinds of psychological states, including orgasm, which is a neurological state where as you go over the edge into that, what happens is unpredictable to you generally. So here's the same thing applied to, for example, energy price elasticity, in that when the natural gas reserve was discovered in Russia, they didn't know what to set the price at. And so the price went from relatively predictable to very chaotic very quickly. Another example is tax, in that how much tax do you put on a people before they quit working and leave the country? And so what is the threshold? And those are a number of countries where they've experimented with how much to tax a people before the citizenry gives up and leaves the country. These singularities happen in stock markets and in economic markets. This, for example, was the IPO day of Facebook. And when it IPO'd, it was in controlled trading, so people couldn't short it. However, this second line is Zynga, which got most of its revenue from Facebook. And so people, when Facebook went public, their automatic trade systems did kick in and short Zynga. And where these blue arrows are where the intervention between the market system and the high-frequency trading AI systems shut them down and say humans have to do this, because the AI systems said this is going down, sell, sell, and they tried it again and it got worse. And so they shut it off for a couple hours, turned it back on, kept it at a fixed price, and then they said, okay, we'll let the market go again. And they didn't know at that point what was going to happen. It's unpredictable. And so that's another example where things go from predictable to not. An AI kind of example is the recent winning by a computer against humans in a game that was thought to be intrinsically human. And in this case, the computer beat the two best Jeopardy players in the world. And Jeopardy as a game requires understanding language and understanding sort of nuance and questions that previously was thought computers couldn't do. They're getting better at an exponential pace, such that fields like medicine and law and engineering and marketing even are something that computers are getting such that they can do those things better than humans, or even groups of humans. So, some time ago, how many people know who Timothy Leary was? Well, he was a professor at Harvard in psychology, and he's sort of the Pied Piper of LSD. And he's the tune-in, drop-out, turn-on person from the 60s. And he died in the 60s, actually. But he had a chart that I found very interesting, that he made by hand, even, of the number of realities we have access to per day. And back in sort of tribal times, when living in a village, you might experience a few stories or a few news from neighboring villages in a day, but it was pretty much limited to one reality. But once books and TV and then PCs and then internet started coming, you can tune into a reality show in Nepal or in France, or you have now billions of alternate realities that you can tune into on any given day. And so this is a sort of super exponential growth of something that people experience in real life. A treatment of what a super intelligent entity might be like was in the movie 2001, where the monolith was considered something smarter than humanity or all humans. And the movie is really about the interaction between those two. And Steve Jobs, who liked that movie, sort of took note of the framing of that when he launched the iPhone, implying that the iPhone was a connection or a gateway to multiple realities and an intelligence greater than our own. Ray Kurzweil's done some forecasting of sort of the evolution of consciousness and awareness into different epochs of physics and chemistry, biology, brains and information, where we've been, technology like phones and internet, where we sort of are, and now this fifth epoch of the merger of technology and biology, where everyone here has at least one phone and at least one computer with them. So we are becoming hybrid electronic biological beings. And the consciousness is considered held in the internet and in the people. And the internet itself may be conscious in a way that we don't understand, in that people say, well, the internet's just electronic, it's simple, it's just computers. But remember, there's 1 billion people in the internet, so it's at least as complicated as 1 billion people plus 1 billion computers plus all the routers. So the next epoch of sort of consciousness is when the planet becomes conscious, and then he forecasts the universe. And then there's a concept of, well, what happens after that? And there's a concept of transcension, in that in complexity, we can be more complex, like launching rockets out to Mars and bigger and noisier and so forth things, but complexity of life is increasing in that way. But Fermi's paradox is, why can't we see other places in the universe where there is people sending rockets and TV and radar out at us? And we can't. And there's a branch point that the transcension hypothesis is that things continue to get more and more complex, but they get quieter and smaller and more intricate. And just as the internet or communications has gone from radio and TV through the air to fiber optic under the oceans, and the chips have gotten more complex and smaller, from a point of view of looking at Earth from far, Earth is getting quieter and more complex. So it's possible from the evolution of life in the universe, there's a trend towards complexity, or the opposite of entropy, but it's it doesn't have to get noisier and visible. It might become more invisible, and those civilizations that have survived are quiet, and we're the noisy ones. So exponential change is sort of the simple way to think of what's happening at an event horizon in singularity. And if you consider the population of the Earth, 100 years ago, there was only 1 billion people. So we've created 6 billion additional people in 100 years. And those people really don't have anything to do. And as we make computers better and systems better and so forth, the population of people is continuing to grow. But there's an expectation that everybody should have a job doing what they used to do, or in the good old days. But consider many people on Earth still have the job of carrying water. And places like here, well, that's been handled by civic works and plumbing, and those jobs are gone. So those people need to think of alternate career paths, like being a fashion designer in Second Life, for something that didn't exist before. So the price for fixing things also is coming down at an exponential pace, which allows solving certain kinds of problems, or problems at scale, billion people type problems, by using one or more of these exponentially changing technologies that are changing, improving exponentially. So a single computer, the power of one brain by, say, 2023, the power of all human brains by 2050, the amount of compute power on the internet is going up at an exponential pace. When the internet gets smarter than all people, what happens to us as a civilization and what happens to us as people is unpredictable. So Ray Kurzweil and various other people have taken the term singularity to mean that transition, the unpredictability of it, and thus the founding of Singularity University, which I'll touch on a couple things. So this is Singularity University is a relatively new thing at the NASA Ames campus, and it has a summer program, a postdoctoral level summer program, where only 80 people are chosen, and the first half is learning about these exponential technologies, and the second half is applying them to a problem that will affect 1 billion people within 10 years as a team project. And some of those projects are things that government should do, or nonprofits, and others are things that make sense to be companies. And I'll touch on two dealing with transportation and biology in terms of case studies by using these kind of technologies to make things smarter or treat something in a different way, like biology. So if you think about matter, physical things, those can be transported with a moving truck and some moving people, or you could print this thing where you want it to go. And with a 3D printing and these sort of distributed matter type of things, knowing the materials that are in this desk, you can do a calculation. Would it be cheaper to send this desk on a rocket to Mars or print it on Mars, or in Boston, for example? So you can physically transport things or deal with things in the virtual world. So here's a simple example of applying an exponential technology, which is phones, to a not so exponential technology, which is cars, which are starting to get smarter. But the extra thought of, well, let's share the cars with phones. And I'm sure most of you are familiar with that. So one of the projects from 2009 was something that became a company called GetAround, which is basically you can share your car via your phone, and you can also on your phone find other cars that are available to drive. Now Uber has done that much better by saying, well, we'll send you a driver with the car, and Lyft has done it a different way, saying we'll send you a friendly driver with the car. But the concept is that the innovation is the phone and the GPS and the mapping and the linking of the exponential of the internet and phone to the cars as they exist now. So one of the things that's happening is people are moving from rural societies to high-density megacities, in that soon about half the people in the world will live in high-density cities. And if you think about the problem of moving matter around in a high-density city, if you look at the freeway from altitude, you'll notice there's a large distance between these cars. It's virtually empty. Now, the people driving those cars might think it's kind of a light traffic or a busy traffic day from their point of view, but from an abstract point of view, this is a very inefficient system. Those cars could be touching each other if they were smarter. And so Google has embarked upon this project to make cars smarter by putting exponential technology inside the car. And the original Singularity project was, well, what if the cars were autonomous and you could call it with your phone. It would arrive, take you where you want to go. You get out, and the rest of it is not your problem. So these things are combining multiple exponential technologies together, and they don't always drop into existing regulation very quickly. So, sharing cars. So the solution to transport of, for example, roads and terrestrial-based cars creates new kinds of problems of congestion, where if somebody's having a heart attack and the traffic looks like that, and you're trying to send an ambulance to help them, that's not going to get through the traffic very well. And most places in the world don't have roads, and people just walk. And some of the infrastructure, the historical infrastructure, is not keeping pace with the population growth. And so the systems are being overloaded way beyond what they were designed to carry, but it seems to work. And so adding the internet to this kind of transport problem, if you consider how the internet packets work, is there's a piece of information, like a bit of Netflix or your email or whatnot, and it has a start and an end and an address, and it goes through routers with a directory of where to go. But basically you're moving a package, a box of information around the internet based on an address. Now what if you could move matter around that way? So the routers inside the internet used to be hybrid biological electronic devices, where buildings which were full of electronics and some humans that would switch things around. And this has gotten smarter to the point where the router now fits in your hand. That's an example of exponential. This is, I imagine some of you have seen curves like this. This is a logarithmic graph, and this is the price performance of computers over the last 100 years. And notice it's been following relatively consistent pattern despite wars and plagues and things like that. There's maybe some natural exponential law. There's others, like this is the speed of wireless communication. So at the time that Titanic sank, the wireless communications was Morse code. And now you can send 4K videos on your phone. So how could you move matter in an information theory kind of way? In that there's various modes of transport, but combining internet thinking with 3D printing to move matter in the same ways it's moved on the internet. So building a distribution system like the internet that is packages, and the packages can fly and on drones. And so dozens of companies have announced this kind of thing, but it's basically the same as the internet, which is the drone picks up the package, it has an address of where to go to, and it delivers the package. The other part of the analysis, though, is it better to move the pieces of this desk or print it over there? And so that's just an algorithm problem. So old linear technology has problems all throughout the world, but many roads are not passable. However, you can fly over them, and whether it's traffic or lack of roads, you can, for certain circumstances, you can get things faster by flying. And then you can extend networks of these things that carry packages, and just like FedEx, they can hand off and move things around in that way. Thus, moving matter by flying it. So these flying robots have historically been pretty simple, but they're getting much smarter very quickly, and now can fly in formations. They can talk to each other. They can coordinate. They can navigate around obstacles, operate in swarms, and so forth. And the types of things, as they get smarter, the types of problems you can apply them to become much easier to solve those problems. So here's an example of drones building a structure with bricks, and the drone knows where to put it. They're flying over the heads of the audience here, So they're relatively confident they're not going to drop the brick on their head. But it can be built, for example, structures with no, just an algorithm with no human intervention. And that could be being built in Chicago or on Mars, on the moon. So that's the exponential improvement of smarter technology solving problems that normally were dealt with in a traditional way. So the router equivalent in matter, moving matter, is here we have humans and electronics and a FedEx sorting center, which is the router for matter. The packages come in and humans sort them now, partially, but that's being completely automated as well. So soon, packages, for example, from Amazon, you order it on your phone, it'll know where you are, and it can tell you where it's going to deliver it. And there may not be any humans in that chain. So there's moving the physical matter, and then I touched on a little bit 3D printing the matter. This is an area that's growing also exponentially fast, in that 3D printers are getting more capable very quickly. One of the Singularity teams called Made in Space built a 3D printer to print in zero gravity, and that just was put on the International Space Station last month. And if you think about printing in space, there's something different in that there's no gravity. So you can print something that's a mile long and it won't fall apart. Where if you were to try and print that on the Earth and get it to space, it would break apart. So the kinds of possible things you can do with these printing technologies create new opportunities. So if you wanted to print life, it's becoming close to possible. So at the moment, you can scan a person and print out a plastic object of them, but there's also ways that you can read life into the computer, move it to a different location, change it, and print it out, and reboot it as life. And this is an area called synthetic biology. So here's a hybrid biological electronic machine, which is a natural frog and a natural phone game, but they're interacting with each other in a natural way. But biology has a different than computers. It has free will. And so a lot of people who study computers, where they're very deterministic, and you can say, I want my program to run this, flow and come out with this result, you can predict that it's probably going to do it. When you're programming in DNA, programming biology, you can make a gene circuit and you feed it sugar and you hope that the biological thing is going to do what your program says, but very often it does something completely different of its own free will. And the more complex the biological system, from microbes to plants to mammals, the more likely it is to do something else with your program. And so programming in biology is very similar to programming in computers, where computers operate on ones and zeros. You use an abstract language that's compiled down into ones and zeros that run on your machine or your phone. Living things run on a 4-base code that's coded in DNA that you can program in an abstract language, and you can print it out and insert it in a cell, and it runs like software in a cell. But the software is encoded in DNA. And so there's a company doing compilers for genomes, and when you've designed your gene that you want to add in, say the glowing genes from fireflies, add it into a plant, just copy and paste, and then say print out that DNA for the plant with the glow genes in it. That's software, and then you send it to a printer, There's a new company in San Francisco is building a DNA laser printer that basically incomes the software sequence of DNA that is requested. The system makes it and FedEx out the actual DNA that can be inserted back in the cell to run this program.
That's Austin, guys. We had Austin City in class.
Yeah.
Cambridge Genomics. That's his company. Yeah.
So I'm the chairman of that company. But it's basically reading life, designing it, editing it, and writing it back out, and iterating. So old manufacturing going to new manufacturing in a cell. So a manufacturing plant that's making, say, chemicals might look more like plants than test tubes. The reading costs, I guess you heard about this, but the reading cost of DNA is going, improving 5 times faster than Moore's law. And the writing cost is also improving, and the objective of Cambridge Genomics is to have the cost of writing DNA be comparable to the cost of reading DNA. So from a DNA point of view, it's like your desktop printer that can scan documents and can print documents. And why this is useful, you heard about this, but basically you can take the genes from one creature, design them, put them into a different creature, and then just grow that creature, for example, beer, to make something that it doesn't normally make. And there's a lot of technology involved in this that Austin probably talked about.
Austin, he didn't actually, he just sat in on the class. He introduced himself briefly, so it's all good.
All right,
sounds great. Yeah.
So there's a few steps. But it's basically an iterative cycle where you end up starting with 2 things and making something that becomes products. And those products you want to test and improve. And I'll give one example is that there's a cosmetic oil that's used in cosmetics called squalene, and the place that it's got now is from the livers of sharks and whales. And so they kill sharks and whales to extract this chemical out of the liver and put it into high-end cosmetics because it works well. And so with synthetic biology, you can take the DNA that was in that shark, sequence it, and then print it into a form that will run in the yeast cell that's in beer. So you would take shark DNA, put it in yeast, brew the yeast as beer, and then the yeast will, of course, make beer, but they'll also make the squalene molecule that you can put into the cosmetics at 1,000,000 times cheaper, and you don't have to kill the sharks. So this has created a new kind of industry, like the homebrew computer club, from which Apple came and a bunch of other cool stuff. There's now a homebrew biology clubs springing up where people are hacking biology, and you start essentially with an idea, and you create a reprogram or hack a creature, and a common one is yeast. So these are a pair of companies, and the investment thesis or the business model of that was basically Microsoft and Intel to create Wintel. So you need an operating system component, which is the compiler, and a hardware component, which is the printer. So the concept is very similar to the software and the tools to build the software. It's just the code is A's, T's, C's, and G's of DNA as opposed to the ones and zeros that run in computer hardware. So this is like the read-write problem. Here's an example of the laser printer and its early prototype working. So it's using DNA is growing 1,000,000 strands at a time. The growing process isn't perfect, so they have errors. So only about 1/3 of the strands of DNA are accurate, and the system uses lasers to knock the good strands off, separating them from the bad strands, assemble them together in genes, and there you have DNA. And so there I've sort of touched on transportation and biology and what singularities are, but these are the other areas that Singularity University concentrates on with these billion people problems in the summertime. So I'll sort of conclude with the thought, if the internet is conscious or alive, does it wake and sleep? And if you think about the billion people on the internet, well, they're awake and sleep. And here's a picture of all the routers on the global internet over a 24-hour period. And you'll notice a blue wave going around the world followed by a red wave of activity. And so the red is basically the internet being awake, and the blue is the internet being asleep. And it's doing both, rotating around the world, more or less synchronized with the people locally who are awake or asleep. And you'll notice in the blue, there's occasionally red spots, and those are like Google data centers synchronizing and the routers, improving the DNS. But for the most part, the activity goes with the wake-sleep cycles of the people.
We might not too much more time. We just play like 2 more minutes.
So I'll leave out the stuff about entrepreneurship because you've already had a class on that.
They have a little dosage on venture capital.
So the key thing is if you want to have a good business, you have to have happy customers. And there's one thing that venture capitalists don't often cover, which is I call $100 hamburgers. Where if you take other people's money to start your business, and the price earnings ratio, say a public company, might be 10 to 1 or 30 to 1 or whatever, but the price earnings ratio of a startup, the cost of getting that money is maybe 1,000 to 1 or 10,000 to 1 or at least 100 to 1. So if you're doing a new company and a startup using other people's money, and you now have raised your first round of funding and you have a bank account, and you go spend $1 on a hamburger, the cost to you as a co-founder of that company on a price earnings ratio is $100. So being frugal with your investment money pays back a lot in the long term. So that's it for questions now.
So we'll open it up to questions. You can ask Reese anything. Yeah.
Hi. I'd like to know, like, a lot of things that you actually talk about, like seniority. I think at the current situation, it's very hard to kind of like justify whether they make money or not. So how do you know whether you want to pursue them? Is there?
Well, not everything. One of the differences between Berkeley and Stanford is about making money. And that Stanford students are very good at that. But there are problems that are important to solve, like stopping the next asteroid from hitting us and wiping out all life on this planet. Well, you could do that in a way that's strategized to make the most amount of money, or you could do it in a way to save humanity. But I didn't understand the specific of your question.
So let's say that you want to solve a problem that is exponential, right? So, but probably like the rest of humanity wouldn't be so concerned about it in the near term, and therefore they wouldn't put the resources together to solve it. Right?
Yeah. So there's a saying that the future is already here in this room, but it's not evenly distributed around the world. And so if you are building something, a solution to a problem, and phones cost $1,000 each, and you're trying to solve a problem like hunger using phones, if you know that the phone is going to get half the cost each year, so $500 in the second year and $250 in the third year, and eventually it'll be free. And so if you use an exponential technology to solve that problem, maybe in the first 3 years it loses money. But in the later years, like photovoltaic solar panels are becoming more and more efficient, where they lose money now, but they are on an improvement curve that will make more money in the long run.
Okay, yeah, I get what you mean.
Yeah.
Okay.
Do you think the end result of the new flourishing of bioengineering and that end goal, do you think that eventually will lead to people changing to themselves?
Yeah, sure. I think programming biology is bigger than the internet and computers. There's a lot of stuff that's live that can be programmed. And the cool thing about it is they self-replicate. The computers don't do that. Like you make one, and it reproduces itself. Did you have a question?
So I had a question about the drones part, where the drones were building the model. So my question is, currently people do that, right? And we saw that people are growing at an exponential rate. So if we start using drones for doing these kind of things, how do you suggest people find alternate jobs? I mean, because people are also growing.
Well, so I sort of poked at that question about jobs, in that if we've added 6 billion people in the last 100 years, we haven't added 6 billion new kinds of jobs. I mean, there weren't software programmers 100 years ago. There were more cattle ranchers there then than there are now. But automation is making the kind of jobs that people don't like to do, like carry water, automating that. And that's a good thing. Like, who wants to carry water as their job? So what the creative process is, how can the humans think of things to do that robots can't do? Because if the robots can do them, they will do them, because they work 24 hours a day, they don't complain, they don't need minimum wage, they don't go on strike. So, you know, the labor, the things that humans dislike doing, will be automated, including legal research and medical research and a lot of things that aren't automatic now. So the creative opportunity is to think of new things. For example, Second Life or High Fidelity or Facebook, which consumes hours of people's day that nobody spent time doing that 10 years ago. And so there's people who create entire industries to fill up the time of the 6 billion people whose jobs have been replaced. And that is a difficult socio-political, economic situation that is probably leading to unpredictable outcome. But the concept of continuing to preserve carry water jobs isn't necessarily the best approach to solving that problem.
Do you believe that there always will be jobs that humans can do that machines can't do?
Well, like the frog eating the bugs, the frog is probably a better friend to other frogs than a phone. And so humans are evolved to interact, you know, in a friendly way with each other. And humans are super highly evolved in mate selection and in friend selection, and whether can I trust that person and or should I fear that person. Those kind of nuances and subtleties humans are especially good at. Computers aren't that good at that yet. So at the moment, the humans are ahead in being a friend. But the computers are catching up on a lot of things that humans don't want to do.
You mentioned companies from Singularity University in transportation and biology, but outside of those two areas, what is one company that you're most excited about?
I like this one, Made in Space, which is making stuff in space. And it's already has stuff up in space doing that. So there's a lot of things that are really cool that they're doing that can't be talked about, unfortunately.
Okay.
But the Singularity's been running for 6 years. There's typically about 20 projects in the summer. Typically about 5 of those make viable startups. The projects are 1 billion people in scale, which is too ambitious for most startups. It took Facebook more than 10 years to get to 1 billion people. But if you divide by 1,000 and say, okay, we'll do a startup that's going to try and get to 1 million people in 3 years, so 1/1000th of a billion, That is a maybe startup. So of the 20 projects per summer, about 5 of those are sort of in the ballpark of a viable startup. So in 6 years' time, there's been roughly 5 per year, so there's about 30 companies that have come out of that. But the purpose of Singularity University is not an incubator, not starting companies. It's more teaching people about this information and how to use it.
Right. Can you talk more about the trajectory of 3D printing? For example, how long do you think it'll take to make 3D print everything in Screw?
Well,
besides that,
faster than is intuitively obvious, because our intuition operates on a linear scale. And the classic example is if I were to take 30 steps, equal steps in that direction, most everybody in the room could pretty accurately guess where I would end up. However, if I were to take exponential steps, like the first step 1, and then the second step 2, and then the next step 4, and then 8, and then 16, and then 32, and then 64, the distance I would travel is over 1 billion steps, and that's 6 times around the world. And so if the technology is moving at that exponential pace, or my steps were going at that exponential pace, it's very difficult to predict how many times around the world would I go, or where I would even what continent would I land on. So it's unpredictable. Does that make sense?
I was wondering about the ethics of synthetic biology. I feel like it's a really powerful technology, which, as all powerful technologies do, has the potential to be abused. So I was wondering what you think some of the most egregious abuses might be and how we could curb against that sort of behavior.
Well, so like all technologies, there's good and bad to it. So fire, you can cook your food and heat your house, or you can burn people and burn down villages and burn forests and stuff. So it's dual use technology. So synthetic biology is basically programming biology. So you can do things to eliminate cancer, or to improve food production, or make chemicals that you have to kill animals or dig up oil to get. A lot of those things can be replaced by this technology, which is a good use. One of the things that we cover in all the tracks at Singularity is policy law and ethics applies to each of these technologies, the good use and the bad use. So bioterrorism and cyber warfare, in order to stop it, you have to learn how to make it. So you have to know both sides, otherwise you can't really have the tools or the wisdom to stop it. And so in the open education view of things, the more people in the world know how to use these tools and stop these kind of things, the faster we'll be able to stop human-induced bad things. But it turns out most bad things come from nature, like anthrax or Ebola or something. There's no human, coding that and sending it out. There's already lots of bad things in biology, and a lot of the work is, well, how do you stop that? Like the vaccine, or not the vaccine, the cure for the first two doctors that came back from Africa with Ebola was a synthetic biology product, and that it was genes from something else that were grown in tobacco plants, and those tobacco plants were ground up and made the serum, and they only had enough for 2 doses, and it cured the first two doctors that came back, and they haven't made enough more. So those kind of things, it's a good question, but ethics applies to everything.
One more question, Reese. I imagine that in any exponential trajectory, your error would grow equally exponentially, right? So my question is, how do you teach or how do you train people to avoid the pitfalls in these predictions that are rather unintuitive?
Well, many people who are trained in engineering or physics tend to think in deterministic ways. And there are many things in life and biology and nature and the world and these exponentially changing things that are unpredictable, meaning they're non-deterministic. So understanding a little bit more about complexity theory and chaos theory and unpredictability is something, if you build into the product, like Apple's been building phones for years, but many of them break. And because when they fall, they just naturally fall on a corner. And so they just announced this week a way that the phone will turn itself and land on an edge and be less likely to break the screen. So that kind of thing, you know, the predicting that people are going to drop their phones, you have to make like millions of them to find out how they're going to break, and then fixing that was hard to predict before you had the data is kind of an example of you know, using solving an unpredictable problem with the data that you gather. If that probably not a good example, but if that makes sense. All right.
Okay, I'm going to excuse Reese. Thank you, Reese.
Thank you.
So, I was really, really grateful that we got Reese on the last day, because Reese for me embodies entrepreneurship in many ways, on multiple levels. You know, if you talk to people now, Reese, people might think about Reese and associate him with singularity. If you guys were around 15 years ago, Natopia was a big, big thing, and everybody associated Reese with that. And the reality is that Reese is like a quintessential entrepreneur. Who he is not a function of any of these things. It's the mapping of his mind and how he thinks about the world and the world at that moment. That's what creates singularity, that's what created Natopia, that's what creates everything else. And really, when you guys are starting startups, that is an event horizon. People get that? When you're crossing, when you're entering into, even just the act of starting a startup is entering into this world of uncertainty. Okay? Even taking this class was a little bit of an event horizon, because it's a fairly different type of class in the sense that it's unstructured. So what I want to do in the final few minutes that we have is one, thank you guys for taking the class, and also just sort of recap a couple takeaways. Were there any takeaways actually from Reese's talk that resonated with other themes that came out during the class? Yeah.
Okay. So like, felt like he was very different from all the other speakers.
Okay.
Like,
No way.
particularly like in his lack of enthusiasm.
His lack of enthusiasm.
Yeah.
And Reese is here.
I know. But the thing is, it's very different because it seems like he's very calm in the way that he thinks of things. He thinks about work in a larger scale.
Yeah.
So it doesn't have any reason to be particularly enthusiastic.
Yeah, and so did that strike you as more authentic, or was that a positive thing for you? Or was it, how did you feel?
I feel like I'd be very calm and secure around him.
Yeah.
Knowing that he has all the answers.
Yeah.
Like that. So like house, okay. It's not, yeah. So I think it's a good thing.
Okay.
Positive.
And was that different than, let's say, Jennifer from New School Ventures? She was calm too.
Very, yeah, in a slightly different way. Yeah.
Okay. Okay. So, anything else? Yes.
I just think it's a completely different way of thinking.
Yeah.
Many times the people that came in told us, don't do a startup because you want to do a startup. But in reality, everyone does a startup because they want to do a startup. It's not like someone forces their hand.
Right.
At the end of the day, that's something they want to do. Maybe they have a company they feel really passionate about. I think Reese's way of thinking is, you know, skating to where the puck is going to be and not, you know, where it is right now, and like looking at trends and how life, or like, you know, people have evolved throughout the past 20 years and seeing where the trend is going and beating everyone to it.
Yes. And you can see when you're looking at the world through Reese's eyes, the idea of how much you're going to lose is trivial relative to what there is to gain.
Yeah.
Right? And the big question that you should be focusing on is how big can my life get? How big can the technology I'm applying impact the world? And the thing that's relatively trivial is what you can lose.
And I think just to add to that, like I think if entrepreneurship was taught in the way that Reese was talking about it today, and not necessarily about, and this is no way related to this class. I'm just thinking in general. Everyone's like, like you're supposed to go and raise funding, and then you're supposed to go and find a partner. Like I feel like that is the trivial thing that you can learn as you go. But if people start thinking of life the way Reese tried, like to describe it in like an hour presentation,
yes,
we'd see a lot more companies that are revolutionizing the way we live.
Yes, and would you have more confidence about starting something?
Yes, exactly.
Yeah, because you're focusing on how big it can get. Yes.
You can have more confidence about starting something as long as there is communications for it. You can make as many apps as you want, but if people don't have phones that support these apps, that's not going to work. So I understand that you're talking about like the TikTok notion, like the big leap and the small leap, but the big leaps are not more important than the small leaps.
I would disagree. I would think I myself would not want to like start Snapchat if you told me, if like I could look into the future and know that I would, the company would be valued at $10 billion. I still wouldn't do it because I don't feel like I'm adding something that's more significant than like Google. Like I would rather start a Google and fail than start a Snapchat and have my company at $10 billion, because in my opinion, making a difference, like Google's, like what's Google valued at right now? Like I have no, like it's a number so big, it's like worth more than countries. Like in my opinion, if people were thinking that way and revolutionizing like the whole world.
So even if you were a solution that didn't have a problem, you would pursue it because the intent would be to at least
add a lot more value.
Okay. Okay. Any other final comments? Yeah, Ian.
I just thought it was interesting that this was I think the only time that what you should do when you get the money from VCs was talked about. Saving money. It was like a 30-second part of the presentation, but nobody else talked about how they spend the funds that they get, and it was something I was really curious about the whole time, but nobody ever really addressed or gave any sagely advice about, okay, you're somebody, maybe you haven't had a lot of money, $250,000 falls into your lap. How do you resist the urges, and how do you manage that? And so even though it was in like 30 seconds, you actually talked about that more than anybody else this quarter. And I mean, just that sort of, it was just an interesting thing.
Yeah, it is interesting, and it's a critical point.
Cash is oxygen. The first company I did grew to 300 full-time paid employees with no investors. So all the money came from the customers.
And that's so when you're starting a company, one of the sacred rules that we touched upon very, very briefly, but is this idea that cash is oxygen, and so preserving that's critical. And you're right, we don't. I think within the rest of the curriculum is very much a venture-backed type of model where you just go down Sand Hill Road and you assume that money can be sold to you. And,
right, but even then, what you do with the money is incredibly important. I think, and nobody else would.
Yes. Good. That's a good perspectives. Okay. So the main point of this class, and the reason why we don't teach it in a didactic way, is the reality about entrepreneurship is that it lies within you. It lies within your unique viewpoint is really where the key asset is. And the very nature of entrepreneurship is about change. So it's not about boxing the unboxable, it's about how do you want to have a relationship with that. So it is very much about going into the unpredictability of the singularity and sort of relishing it. And ideally, when you see these things, it can be confronting and scary if it feels like it's being done unto you, and I'm going into this unwieldy world that I have no control of. Or it can be empowering and exhilarating if you can get off on it. So, and really, when you're looking at entrepreneurship today, the classic academic definition is it's about the pursuit of opportunity beyond resources controlled. And when you throw yourself into that environment, what that means ultimately is that the individual and the individual's idiosyncratic interests and expertise become critical in that situation, because it's not really about any specific resources that you have. So I'm going to so having said that, I'm going to give you a couple takeaways. That even though I say that everything is really about you self-creating the world, let me give you a couple takeaways from this class. But the biggest takeaway is to know that this is an ongoing exchange. And even though the class is sort of over, really your paths are just beginning. And so as you weave in and out of entrepreneurship, I'm always accessible. So I'll send, everybody has my email, but you can email me or any of the TAs. I'll also share Reese's email if he's interested, so that as you guys go down the path, you can tap it. But the first thing is, I think the first theme is that because the individual matters so much, do what you love, okay? And do not only what you love, but do what you uniquely love. And this is, going back to Peter Thiel's classic question of what do you know to be true that few people would agree with you on? That is the light towards what your key asset is to give to the world, because that's your source of competitive advantage. You can love technology, okay? As we saw with the co-founder of Nest, Matt, he loved technology. He knew when he was a kid that I just want to work at Apple. That was his clear guiding principle, his love. Or Tina Wells, who just from college loved going after teenage the teenage marketing, okay? You can love technology, you can love markets, you can love people. It can be like, I just love to work with this type of a person, and I don't care what I'm doing, but that's what I know that I love, okay? But you need to find something that you love, and you ideally want to find something that you love uniquely, and then play hard on that one thing. Drive that as your competitive advantage, okay? And I thought Ben Horowitz's words were really wise when he said, it's going to take you as much effort to fail as it will to succeed. So you might as well succeed. Does that make sense? So if you're going to go, you might as well go big, because it's not more work to go mediocre, and it's not even more work to fail. In fact, it can be easier to go big. Not only because of these exponential technologies, but there's more resources available to you if you go after a bigger vision. So if you're going to do this, just go big. And the first thing is that everybody in this class is a leader. So when you saw throughout this whole class, including Reese, everybody is a leader, but they're a leader in their own unique way. You know, and some might present to you as non-enthusiastic, but then their brilliance comes out in other ways. And we've seen leaders that are profoundly introverted, leaders that are profoundly extroverted. The key thing to be a leader is just to know where you're weak and know where you're strong, and find the others that are as good at what you're weak in as you are in what you're strong in. Okay? It's not about finding others that are just better than you in what you're weak in, but find others that are as good in what you're weak in as you are in what you're strong in. And so know who the rock stars are and round out that team. And we saw that with Julie and Kevin Hartz. Okay? They happened to start Eventbrite. They could really have started anything, because if you notice the two of them, that marriage is partly because they're so different and they work together, right? So know where you're weak, and it doesn't matter what you're weak in. It just matters that you take ownership of it, and just whatever insecurities you have right now, just drop them. Okay? Whatever they are, just drop it and move forward. Okay? And just take ownership of it, and that's how you'll own that. And then the final thing that you just have to do is just figure out how to make money. Okay? So find out what you love, find out how to build that team around it, and figure out a business model that will get you cash. Now, if you need cash before you have a business model, you have to go knock on the VC's doors. Okay? And we talked a lot about the mechanics of venture capital. And at the end of the day, when it comes to any there's a whole getting into venture capital, like we heard earlier this week, it's sort of like the VC's job is to sell you money. Okay? And so if you're going to be sold money, make sure you want to buy that money, and understand what comes with that money, and how the VC is motivated to make that money. And also understand that whenever you go into any negotiation, the key to negotiations is put your attention on the other party and understand their interests first. Whoever does that first wins. And there's a distinction between the positions of the negotiation and the interests. Once you understand the other person's interests, you can then manipulate the positions to come up with a transaction that works. And there's good transactions and great transactions. The good ones are just anything that's open that Zopa. And the great ones are ones where the other person gets theirs open, you get even more. Okay? But if you can get a business model figured out, that gives you then the currency to actually do what you love. And that's the lock that you have to unlock to not take the job that you might not want to take, but you feel like you have to. Okay? Once you have that figured out, the key things when we're talking about building products is, there's a whole everybody's talking about customer development these days, but if you remember back to the design thinking experiment that we did in class, I want you to use customers as a way to validate that there's a need, but not as a way to determine how to construct the solution. So the solution comes from your heads, the solution comes from your team, the solution comes from the unique insight of entrepreneurial creativity. The customer development validates that there's a market, that there's an opportunity to go after, and that's really where the magic happens. And then when you're crafting the business model, try to do it in a way where you'll be cannibalizing your competitors, where if your incumbents try to replicate what you're doing, they will kill themselves. Okay? And so that's the other unintuitive insight I think that's come out this quarter is that the technology enables the disruption, but the business model is really the driver. Uber could have existed 2 years ago technically with phones. You could have had people calling up and connecting people in. but the price points and the volume have now become so disruptive that the thing's taken off. So think about the market timing there. And then the final thing I would say is that you don't need to do entrepreneurship. So one of the most entrepreneurial things is to say entrepreneurship is not for me, okay? And that's perfectly fine. The goal in life is to enjoy life, okay? And to think about what you need to have a happy life, and to think about, in my mind, it is balancing those three things of doing what you love, doing what you're good at, and making money. That's at a simple level. Those don't all have to come from the same source. You can separate those out in your life, but make sure that you have that three-legged stool situated. And if you don't feel like you're lit right now, if you don't feel like, I am the next Reese Jones or I'm the next Matt Rogers, my advice would be to go get your flame lit. So go find somebody else who is lit, and they will light your flame. All of you guys have a flame inside. All of you guys know it. And if you're not in touch with it, your life experiences will force you to become in touch with it, either through good or through bad. Okay? And usually it's through bad, which ultimately becomes very good. Because you'll hit your cauldron, you'll hit your rock bottom, and you won't do it. You'll take the job that you should, but not the one that you love after college, and you'll come home and you'll be depressed, or something will happen, and then you'll be forced to change. That's just the world nudging you towards that fire inside, okay? And you guys all probably know it at some level now, and it's just a question of finding it. And if you don't have it, if it's not there, go find somebody who does have it and just work under them for like a year and a half, okay? And that's why PayPal created all those amazing startups. And so my hope is that you will find that flame and it will get lit, and it happens at different times in life. But when it does happen, people don't go back. Okay, and that is where the adventure lies. It doesn't lie in the outcome; it lies in that process of that discovery, of that perpetual discovery. Okay, so thank you guys, and that's class. That's the year.